Okay, we're back for part 2 of the notes. Now we're on the back page. And now we're going to talk about inverse functions. The idea of an inverse. You do this all the time when you solve an equation. Okay, for example, if you have 3 times x is equal to 15, the way you solve that is you undo multiplication. You divide by 3. That's the inverse operation. If you have an equation, x squared is equal to 16, the way that you undo a square is you do the inverse, which is the square root, and you get x equals plus or minus 4. So the key word is that inverses undo each other. They undo each other. The idea basically is what happens is you switch x and y. So if you have an ordered pair x comma y, in the inverse function it becomes y comma x. So with an inverse function, what happens is you're going to switch your x and your y values. So for example, number 4, f equals, so this is function f, and it's a set of points, 2, 5, 1, 2, 3, 6, negative 1, 4. So each one of these is an ordered pair x comma y. Write the inverse of this relation. Well, 2 comma 5 becomes 5 comma 2. 1 comma 2 becomes 2 comma 1. 3 comma 6 becomes 6 comma 3. Negative 1 comma 4 becomes 4 comma negative 1. Now the thing is, if we graph these, okay, let me graph f first. So 2, 5, 1, 2, 3, 6, and negative 1, 4. Now I'm not going to connect them. This is just a set of points. Now let me also graph the inverse, and the way that we write this, by the way, f, and then we put a negative 1 almost like an exponent, and then this is a set, okay, so it's a set of points. F negative 1, that is f inverse. So you're not raising this to the negative 1. This symbol here means the inverse of f, the inverse function. So 5 comma 2, 2 comma 1, 6 comma 3, and 4 comma negative 1. Now it might look like it's kind of random, the points, but what happens visually is that if I draw the line y equals x, okay, if I draw the line y equals x, notice that these 4 points are going to be symmetric to these 4 points across this line. This is a line of reflection right here. And the points will be symmetric across that line. So these 2 points go together, these 2 go together, these 2 go together, and these 2 go together. So one of the properties when you graph an inverse function is they will be symmetric to the line y equals x. That you could fold these 4 points, take them, fold them across the line, and they'll put you onto these 4 right here. So that's always going to be true. And again, the idea is that inverses undo each other, and what happens is when you switch x and y, you're going to create this symmetry relationship. So let's say we have in number 5, graph g inverse. Graph g inverse. So here's g of x. Here's the function we're starting with. Well, the points, if I label them, are 0, 0. This is 1, 1. This is 2, 4. To graph an inverse is you're going to switch x and y. So 0, 0 will stay the same. 1, 1 will stay the same. However, 2 comma 4 will become 4 comma 2. And if I connect them, it's going to look something like that. So that's g inverse of x. If I draw the line y equals x, assuming I draw it somewhat accurately, then notice again that these 2, they're symmetric with the line. You could reflect this onto here. They reflect onto each other. Now you don't need to graph the y equals x. This is the key right here. But in terms of the visual, inverses are always symmetric to y equals x. They're always symmetric to y equals x. If you want to find an inverse, what you do is you switch x and y, and then you solve it for y. Okay, so let me give you a couple examples of this. Find the inverse of f of x equals x squared. Now, you already know, because we just talked about it up here, that to undo a square, you square root it. Let's see if that's what comes out of this. So we've got, I'm going to write this as y equals x squared. Okay, f of x, same thing as y equals. To find the inverse, what we do is we switch x and y. So that means I'm going to write this as x equals y squared. To solve this, I want to solve it and get it into y equals. I have to undo the square. Well, the way we do that is we take the square root of both sides. And what we get is, I'm going to put the y on this side. Y equals, this will be square root of x. Now technically it would be plus or minus, but we're only going to keep the positive side. Okay, and the reason for that is we need to keep this as a function. And if I take the negative side, this would not be a function. So it's just y equals positive square root of x. So in other words, the inverse of f of x is square root of x. Now remember that the idea of inverses is that they undo each other. Okay? So the inverses undo each other. If I square a number, but then I square root it, I go right back to where I started from. So inverses undo each other. And what happens as well, if I try to do a composition, f of the inverse of x, composed with the inverse function of x, I would start with f inverse, which was square root. So that's the square root of x. If I go to f, which was x squared, look what happens. The square root of x squared is just x. When you do a composition of inverses, you're going to be left with x. And in terms of the visual, y equals x, right? Where 1, 1, 2, 2, 3, 3, where they're the same. Okay, so algebraically, when I do the composition, I'm going to end up with just x. I'm going to end up with my original value that I started with. Visually, when I do a composition, they're going to be symmetric to the line y equals x, right there. So let's do one more here. Let's take number 7. Find the inverse of g of x equals 3x plus 4. Now I'm going to start again by writing this as y equals 3x plus 4. When you find an inverse, we're going to switch x and y. So I'm going to rewrite this, x equals 3y plus 4. Now to solve this for y, we're going to go minus 4 on both sides. You can't combine this, so we just write x minus 4 equals 3y. And then our last move is to divide by 3. Now when we do this, I'm dividing this whole thing by 3, so I'm going to break it up and just take each term and divide by 3. So what we get is, again, I'm going to put the y equals on the left side. Y equals, this is x over 3, or you could think of it as 1/3 x, and then minus 4 over 3. Y equals 1/3 x minus 4 over 3. So I'm going to finish that off. I'm going to say g inverse of x equals 1/3 x minus 4 over 3. That's my inverse function right there. Now just to show you that these are actually inverses, if I go to y equals, and if I type the original function, 3x plus 4, and if I type my inverse, 1/3 x minus 4/3, when I graph them, I'm actually going to go zoom square. You could do zoom standard. There's the first one. There's the second one. And if I also go y equals x, which is that line of symmetry there, look at that. Look how this one would fold right onto here. So visually, I can tell that these are inverses. If I go to the table, well, let me start at 0 here. Go to the table. So I've got 0, comma 4. That was for the first function. Now the inverse, 4, comma 0. Okay, the points reverse. 1, comma 7 for the first function. The inverse should be 7, comma 1. Yes. And let me go back and do number 6 as well. So we had y equals x squared, and then y equals square root x. Let me try zoom 6 here. Y equals x squared is a quadratic. Now notice that by doing the square root of x, what happens is that this is symmetric to this piece of the function, but not to this piece. If I had also graphed y equals the opposite of the square root of x, I told you before, we're only going to take the positive square root. Here's the reason why. When I graph this, this is not a function, because by the vertical line test, it goes through in 2 places. So the idea of an inverse function, it has to be a function. So when we do this, we would only pay attention, y equals x squared, only the part starting from 0, 0. What we call a one-to-one function. There's a horizontal line test. If it goes through in 2 places, it's not one-to-one. So you would only look at this part where it's increasing. And then for the inverse, I would only look at this part right here. There's the symmetry. Zoom square makes it a little bit easier, I think, to see the symmetry. Okay, that looks a little bit better. Okay, and that's the end of the notes.